We're given the function f of x is equal to x to the third minus 2x squared plus 3x minus 4, and asked to use Newton's method to approximate a zero between x equal 1 and x equal 2, such that the error is less than 0.001. Now, if you graph this function on your calculator, you will quickly discover that there definitely is a zero between 1 and 2. And if you try to trace to it, you'll discover that it doesn't look like it's a particularly nice one. So what we're going to do here is use Newton's method, and let's start with x sub 1 is equal to 2. We could use either 1 or 2, but in looking at that picture on the graph, and if you look at it, it looks to me like it might be a little closer to 2 than 1, so I'm going to choose 2 to see what I can do to approximate it. And then we're going to remember that Newton's method says that x sub n plus 1 is equal to x sub n minus f of x sub n divided f prime of x sub n. So we're going to need to use our number, in this case 2 to begin with. We're going to need to use our function. We're also going to need to use the derivative. So let's note that the derivative, f prime of x, is equal to 3x squared minus 4x plus 3. And what I'm going to do is I'm going to flip over to the calculator, and I'm going to show you a way that you can do these kind of calculations fairly quickly with the calculator and maintain a really high level of accuracy by not having to round anything. So let's flip over to the calculator here for a moment. Now, I've already gone ahead and in the y equals menu put in both of these functions. So in y1 I've put in x to the third minus 2x squared plus 3x minus 4, and in y2 I put the derivative 3x squared minus 4x plus 3. And then in y3 I've created a function which is y1 divided by y2. Let me cursor down here for a second to y4 so I don't mess anything up. If you want to use existing functions and essentially do kind of an algebra of functions thing with them, on the newer calculators you can press alpha and press trace, or the F4 key is really what we're doing, and it'll give you access to all of these different things here. If you have an older calculator, it's a little bit more complicated to find, but you can press vars, you can go to the yvars menu, and then you can choose the function. And there's where you'll see all of those. So you can do exactly the same thing on TI-83 Plus as you can on the TI-84 Plus CE and all the calculators in between. Just depends on exactly what series of keystrokes will get you to these values. But the y1 over y2, if I go back here to the y equals menu, that gives me the f of x sub n over f prime of x sub m part, since y sub 1 is f and y sub 2 is f prime. So we're going to make use of this to make our work pretty easy, and I'll show you how we can use these names to evaluate this quotient very easily. So I'm going to quit back out to our main screen. What I'm going to do first is I'm going to start by taking 2, our first value. I'm going to store it into the variable x. I want the calculator, when it sees the letter x, to think the number 2. And then I'm going to use Newton's method, and I'm going to say that we're going to take that x value and we're going to subtract the quotient evaluated at that x value. So I'm going to pull up the y3. So for me it's alpha and then the trace key, and I can choose option 3. And then in parentheses I'm going to tell it to use whatever value x has in it to evaluate. So that will go through and it'll plug x into y1, it'll plug x into y2, it'll divide, and it'll give me exactly that quotient back. Now I don't want to lose this value, so I'm also going to press store again, and I'm going to store it into x. So I'll lose the 2, but x will become my next value, and since Newton's method is an iterative method, the new value is the input to the next iteration. So I'm going to press enter, and I get 1.714285714. So this is my x sub 2, if you will. Now, obviously, much bigger difference in these two values than just 0.001. I'm going to press enter a second time, and it's going to repeat what you just saw. But now it's going to be using 1.714 as the x value, and I get an x3, a third value of 1.653. Now that differs in the tenths place, so we're not within 0.001. We haven't reduced that error yet, so we can repeat again. Now I get 1.6506. This is x sub 4 in Newton's method. So x sub 1 is 2, x sub 2 is 1.714, etc. x sub 3 is 1.653, etc. x sub 4 is 1.6506. Difference in the thousandths place of 3. So we're not down to less than 1 thousandths yet, but we should be on the next one. Here's x sub 5, 1.6506, and we've got to go all the way, not to the third, not to the fourth, but to the fifth decimal place, and we're not seeing a big difference there. So we finally have gotten ourselves to where our error is less than the 0.001, and we can say that this looks like this number is about 1.6506. So if I flip back to the problem, we can write down that x sub 5 was 1.6506. We could write more decimal places if we wanted to. We weren't told how many decimal places to provide, but I think those 4 that didn't change at all and both numbers rounded to this, I think that's a pretty good choice for an answer. We could continue going until the numbers are exactly the same, that is to the 8 or 9 decimal places that the calculator gives us, but I think this is enough for what we're trying to accomplish here. This is, again, an approximation. It is not an exact value. Newton's method only approximates the 0, but it approximates it to whatever level of accuracy you want.